after this is a flow velocity after integration is represented by uppercase letter U and capital U and capital V. Incident incidentally, eta is here. Eta is here. Is the amount of change in the water surface. Okay. Then by specifying boundary condition for the water surface and seabed and performing the specific vertical integration like this one and apply the boundary condition. This is a kinematic free surface boundary condition, and this is a sea bottom boundary condition. So finally, we get this kind of equation. This is from three-dimensional mass conservation equation. This is one of the governing equation. Okay. And next, I will talk about the equation of motion. Equation of motion. Okay. Equation of motion. So I told you in previous slide I talked about vertical hydrostatic pressures. We assume the hydrostatic pressure in the direction, and also in X and in Y direction. So we need to express the equation of motion like this one. This is X. This is the equation of motion for in X direction. So we after in this equation we try to integrate this equation of motion from sea bottom to water surface, and we also use Leibniz rule. So we get this kind of equation from X direction of equation of motion. Okay. And here, this equation includes tau. Tau is tau is a shear stress acting on water surface and acting on sea bottom. Okay. Okay, and this is a z direction equation of motion, and also we integrate this equation with using Leibniz rule. And after applying the this equation in y direction also includes tau, shear stress on the surface and shear stress on the bottom. Okay. And these two equation motion is also the governing equation. Okay. So these are the summary of the governing equation. Upper one is governing equation for mass conservation. And second one and the third one is governing equation from equation of motion. Okay. So U and V, capital U and V are the horizontal flow velocities, and eta represent amount of change in the water surface as the tsunami propagate. Okay. And generally, we neglect the shear stress on the water surface. Okay. So after simplifying the equation, we will get these two equations. And I told you that the shear stress on the water surface, tau, here and tau here can be neglected because shear stress is much smaller than the shear stress on the bottom. So based on this equation, so we try to solve these governing equations with using computer, okay? So next is a numerical scheme. So again, so this is a equation of motion. And sorry, this is a mass conservation equation. And these two are the equation of motion, okay? And C bottom friction in X and Y direction, we sometimes express these terms with using horizontal velocity U and V. Okay, the shear stress correspond to the square of horizontal velocities, like this one. Okay, and so we replaced U times H plus eta. This is a total depth D. U times D is expressed as M, and V and times D expressed in N. And we will get these three equations to solve the numerically. Okay. This is a grid, example of the numerical grid. In order to solve these three equations, we discretize the space x and y with using the grid. And each grid has a number from I minus 1, I plus 1, j minus 1, j plus 1. And we define the horizontal velocity m and n on each boundary on the grid, here and here for m, and here for n. And the center of the numerical cell here, we define the water surface elevation eta. And the grid has a space with delta x and delta y. For example, so this equation, this is a mass conservation equation. This equation is discretized in time and space. I and j identify the space, location of the cell, and k plus 1, and these are the time step. The numerical computation start from t equals 0, and we try to get the physical value eta, m, and n on each time step. Okay. After discretizing the equations, momentum equation, this one, and the mass conservation, this one. After discretizing these three equations, we compute the tsunami propagation on each time step, okay? So this is, I will show you again the same movies here. In this movie, you can see the water surface elevation, change of the water surface elevation in color. And red color is a higher wave. So these change of the water surface in each time steps is obtained from a numerical computation based on the long wave theory as I mentioned here. Okay. Okay. Okay, and next is advantage and the problem of numerical calculation. There are many advantages in numerical calculation. Here I summarize some advantages. First one is, of course, results can be observed by changing various condition settings. We change the boundary condition and the initial condition, and we can get results with using these conditions. And second one is various physical quantities such as pressures and flow velocities can be obtained uh, at any location at any time. Okay. And last one is a future phenomena can be predicted without being without being bound by the similarity laws that are problematic and model experiments. Okay. This is a very important point because I think you know the Froude number and Reynolds number. These are the important number in hydrodynamics. And these are the definition of the Froude numbers. For example, spatial scale is 1 to 100. So under this spatial scale, time scale becomes 1 to 10. Okay, this is an example of the similarity laws. Okay, so Froude number is sometimes used in the physical experiment, which the gravity is dominant. Okay, gravity force is dominant. And this is a definition of the Reynolds number. Reynolds number is very, very important in case of viscous fluid motion. Okay. But it is difficult to satisfy both at the same time. Okay. So, but when we use a numerical computation, so we do not need to downscale the model. We can compute in the prototype scale. So we do not consider we do not need to consider the Froude similarity law on the Froude number and Reynolds number. This is a major advantage. And also, there are some problems. Okay. First one is the calculation error can becomes a problem if the calculation scheme, grid size, and calculation time step are not selected appropriately. So in previous slide, I show you the grid and cell. So this is related to the time step delta t. So we need to select a time step delta t carefully with considering the space discretization delta x and delta y. And second problem is phenomena smaller than the grid spacing cannot be reproduced. And so we need to use grid and cells. So smaller phenomena cannot be expressed, such as turbulent flow or the boundary layer problem. Okay, and the third one is it is difficult to properly represent turbulent flow field and chaotic phenomena. This is related to the problem in number 2. Okay. So the numerical calculation has some advantages, but we have to be careful when we use numerical calculation because the numerical calculation also includes some problems. Okay. Okay, so far I have talked about the numerical calculation based on the long wave theory. Next, I'd like to talk about the different type of numerical calculation. Okay. Here I will introduce a simulation using a calculation package called CAD-MATH. Unlike long wave theory, CAD-MATH is a method of solving three-dimensional Navier-Stokes equation using a finite difference method, and is also known as direct simulation. Perhaps Professor Fadley may have already introduced this, but this calculation method can simulate the tsunami propagation as it passes through the complex topography and mangroves vegetation. Professor Fadli is actively conducting research into utilizing local non-reach in Indonesia to reduce tsunami disasters. One example of the result of his research is a reduction of tsunami inundation energy by a reduction of the tsunami inundation energy by the modification of coastal topography based on local wisdom. Maybe you already know this research output, okay? And in his research activities, this calculation is as shown in these figures, it is possible to reproduce the way in which a tsunami changes its waveform, and it travels through complex topography, including coastal vegetation. It is then possible to consider the best combination of the coastal vegetation width and density, and the shape of the coastal topography. Of course, the calculation can also determine the flow velocities and pressures acting on coastal vegetation. Okay. Okay. Here is one of the results. Maybe you can see the conclusion. So here, and also today, so I gave you the handout, and please see the handout and confirm the conclusion, okay? And next, today, so I will show you another case of the tsunami propagation. And this also use the CAD-MATH and also use EERC fiber. EERC fiber is this is one of the package software which simulate the structure. Okay. So this is one of our research output. The title is Analytical Investigation of Slab Bridge Damages Caused by Tsunami Flow. Okay. So tsunami caused by Tohoku earthquake in 2011 had brought fatal damages on many kinds of infrastructure such as port, road, bridge, lifeline, and other important structures. Okay. So among those damages, we have found many bridges whose superstructures was flooded away by tsunami flow. This study proposed composite simulation in order to investigate the damage or breach caused by tsunami action. Okay. So in this research, so we use CAD/MATLAB here to simulate the tsunami flow, and also EERC fiber to simulate the structural damages. Okay. And the purpose, proposed method is applied to the damaged bridge whose superstructures was flooded away by Tohoku earthquake tsunami. Okay. Here, this is a photo I show you here. So as shown in this photo here, this is left-hand side is before flooding, and the right-hand side is after flooding. You can see here the small bridge here, but after flooding, this small bridge disappears on these photos and moved on to this another bridge, highway bridge. Okay. This is the results after flooding. Here is a bridge. Here was a bridge, but this bridge was moved onto another highway bridge here. And this is a photo of the flooded bridge. Okay. So we investigated what kind of tsunami forces acting on this bridge and what happened during flooding, okay, with using EERC fiber. Okay. This is the size of the bridge. Bridge was fixed with an anchor number 1, 2, 3, 4, 5 here. And the bridge has 4.8 meter width and 19 meter length, and weight is 1,500 kilonewton. Okay. So first, we use CAD/MATLAB 3D to calculate tsunami wave forces acting on the bridge. The figure on the upper left shows the calculation condition. Here, this is a calculation condition. And the figure below is input tsunami waveform. The tsunami height is around 2 meter height. And the velocity is 5 meter per second. 5 meter per second. Okay. And this is a result of the tsunami propagation. Okay. There are 2 bridges here. This smaller bridge is flooded by tsunami forces. Okay. This is a tsunami pressure acting on middle of the front side and middle of the rear side, and the tsunami pressures act on the bottom and the upper face. So we can get tsunami pressure on many points on front side, rear side, upper side, and bottom side, okay, bottom face. And with using these output, time history of tsunami pressure, next we did a simulation based on the EERC fiber. This is, okay, I skip this one. So this is a model of the EERC fiber, okay? We put the wave force, wave pressure on bottom side and upper face, and also apply the pressure on the front side. And we use ERC package, a model of structural analysis based on fiber model. Okay. Okay. And this is the results. Sorry. These are the example of wave forces applied on the computation node in structural analysis, tsunami pressures. And these two diagrams show the vertical load acting on each anchor. Anchor is here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and how the dead load act on each anchor. This is results on vertical reaction, uplift action, and this is also the vertical reaction, upload action, and on this anchor, this is anchor number 5, and this is also anchor number 5. So these anchors, the load acting on each number 5 anchors exceed the dead load here. This means that the anchors was broken due to tsunami forces and flow up and moved onto the moved onto another bridges, okay, like this one. Okay. So this is a very advantageous techniques to simulate the structural damages caused by tsunami action. This is our conclusion. Here, these studies employed Katomasoft 3D in hydrodynamic analysis and also employed ERC fiber, which can be simulate elastoplastic system with a fiber model, okay? And the validity of the numerical results obtained from Katomasoft 3D was checked by hydrodynamic experiment. And we confirmed that the computed tsunami pressures on the slab show fairly good agreement with experiments. Okay. And also these studies discuss the new mechanism of damages on superstructures of bridge through structural analysis. The structural analysis was conducted by applying the time history of tsunami pressures on the slab, where the pressure was obtained from hydrodynamic analysis with using Katomasoft 3D. Okay. And the structural analysis revealed that the uplift force acted at anchor from number 3 to number 5 during tsunami action. Okay. From the investigation of reaction at each anchor bar, it was assumed that the seaside section of the slab was lifted at first. The location is number 5. and the slab was flooded onto the adjacent highway bridge with counterclockwise rotation during tsunami action. Okay. And also in these studies, the horizontal force act on the investigated slab seems smaller than yield stress. Okay, but the damages of some anchors bar at number 1 and number 2 was observed after the slab was flooded due to tsunami. Okay. The structural analysis revealed that only the anchor bar at number 1 and number 2 support the slab, and the anchor bar from number 3 to number 5 could not work as a bearing section because the seaside action of the slab was lifted up due to tsunami action with counterclockwise rotation. The number of effective anchors bars decreased during tsunami action, and it causes the damage of some anchor bars. Okay, this is very advantageous techniques. We combined the hydrodynamic computation with structural analysis. So only using the CAD mass surf, so you can get a tsunami propagation. But the CAD mass surf also provide you many information. Wave pressures and water surface, change of the water surface elevation. And these can be used to the structural analysis as an input condition, initial condition. So, and after performing the structural analysis, we can estimate how the structure had damages due to tsunami action. Okay. Okay, today, so I show you the long wave theory. This is a little bit boring talk, but please understand the numerical simulation is based on the complicated mathematical formula. And I recommend you to understand what kind of numerical techniques is used in each numerical computation. Okay. And in addition to this, so I want to emphasize the use of the hybrid analysis. Today, so I show you one of the example using CAD mass surf and using ERC fiber. These are very advantageous techniques to investigate why the structural damages has occurred under the tsunami action. Okay. Okay, that's all today's. These are the today's materials, and I want to close my class. Okay, thank you very much. Today, okay.
Sensei, maybe
Huh.
student want to make some question.
Okay, okay, please.
Everyone, if you have question, please give a question to Murakami Sensei.
Little bit boring talk. I'm sorry.
No, nice. I have question, Sensei. I asked about the simulation in the what is the coastal area. That is in Miyazaki, maybe in the video that you showed to us. What kind of software that you make the simulation?
Inundation simulation. this is not a package software.
Uh-huh.
So we write the source code of the program by
Mm,
ourselves
mm,
based on the long wave theory. Today I show you.
mhm.
And we got results, and we put the results on GIS software to animate the tsunami inundation. Okay. So
Okay.
this is not a commercial software. This is
Yes, okay.
our own.
Yes, yes. Okay, thank you.
Okay.
Very interesting.
So I would like to recommend you to do a coupling analysis,
Uh,
hydrodynamics and structure.
uh,
So this is very advantageous techniques to simulate what happened, what kind of damages occurred during tsunami inundation. For example, so you sometimes analyze mangrove vegetation to reduce the tsunami energies, but what
mhm,
kind of pressures and what kind of forces and what kind of deformation that trees will have. Okay.
mhm.
Uh, this is one of the example. Okay.
Yes.
I recommend you to collaborate with researchers which use structural analysis. Okay.
We the problem with hybrid uh experiment, which mean we don't have a laboratory
Yeah,
to
yeah, yeah.
make some experiment like that.
Mm. But CAD Surf 3D and CAD Surf 2D, these are these soft packages are already authorized by many researchers and many engineers. Maybe you can use Surf 3D or Surf 2D without without confirming with hydro hydraulic experiments. Okay. Okay. I think you can use Surf 3D directly. Mm.
Yes,
Mm.
of course, yes.
Uh-huh.
Okay.
Okay. Mm.
Student, maybe you have any question?
Okay, yeah. If you have some questions, please send me by email or Fadori-san, please give me a student question. I'm going to ask the questions, okay?
Hi, Sensei.
Because today's talk is a little bit complicated and a little bit boring, so maybe
No, it's
I
very
gave you
nice.
the handout, and please check one by one. And if you have some question, please ask me. Okay.
Sensei, I send you draft of manuscript. Maybe you have any comment to the manuscript for journal. Please give
Ah,
me some
yeah.
comment.
I'm sorry. So I have no time to read your manuscript. So maybe this week, so I have the time to check your manuscript. So at that
Yeah.
time, so I will give you the comment. Okay.
Okay, okay. Thank you, Sensei.
Thank you very much.
Hi.
Hi. Okay.
Moderator tadi. There are some moderator that start this discussion, this class.
Mhm.
Okay, maybe we can end the class. Thank you very much for
Thank you very
Murakami
much.
Sensei.
Okay. Thank you very much.
Uh,
Uh,
yes, keep in touch. I will send you another email for
okay.
confirmation.
Okay. Thank you.
Okay,
Thank you.
hi. Thank you, Sensei.
Okay. See you.
Thank
See
you,
you.
See.
Pak.
Hi, Sensei. Bye
Bye.
bye.
Bye. Bye. Bye.